So today the topic we're going to look at is what is called expected value. Now, I hate to use the term common sense and math at the same time because it doesn't always go together, but expected value is kind of, it's almost the oh duh of what we're doing. I'll give a simple example. I'm going to flip a fair coin. I'm going to flip it a whole bunch of times. I'm going to flip it 1,000 times. You'd say, I expect 500 heads and 500 tails. That just seems reasonable. Now, the actual probability of getting exactly 500 heads and 500 tails is not very high because I could get 499 or 498. I could be really close. But to say I expect the coin to land heads half the time, that seems like a reasonable statement. And in fact, mathematically, it's absolutely correct because that's the probability. So expected value is kind of like saying, if I do something and all of the probabilities I know ahead of time, can I say what I expect the outcome to be? Yes. Does that mean that's the outcome? No, it means it is the most likely outcome. And that's really the key. If I flip a coin 2 times, I can get 2 tails. I can get 2 heads. I can get 1 head and 1 tail. The most likely outcome is 1 of each, but that doesn't mean I will. But really what that means is over the long run, you tend to see the expected outcomes. In mathematics and statistics, this is generally called the law of large numbers. Some of you may have heard that term before. If a probability is fixed of something occurring, then if that thing occurs over and over and over and over again, you tend to see that particular outcome that many times, the probability. So I want to look at the rolls of a dice, just really simple. So if I rolled the dice 1 time and then I looked at the total, what is the most likely outcome? In other words, what should I expect? Well, obviously there's 36 rolls. There's 11 different sums, 2 through 12. So I could roll 1-1. 1-1 is just as likely as 6-3. Every single one of these 36 outcomes is equally likely, but not every one of the sums is equally likely. So if I said, let's take each of these outcomes, each outcome has a 1 in 36 probability, and then we could go from there. But there may be an easier way. So I'm going to use the language of statistics in this. And so what we do with expected value, the first thing is we identify something called the random variable, which is kind of funny because it is neither random nor technically is it a variable. The random variable basically is the finite list of possible outcomes of your thing. So in this case, if I'm looking at sums, my random variable in this case, and we use in stats, when there's only one, we usually use a capital X. If there's a second random variable, we'll use a capital Y, and so on. So the random variable in this case would be, oops, can't write today, 9, 10, 11, 12. Okay, my random variable would be all the possible outcomes of rolling the dice and then adding them together. Okay, so the first thing in any experiment of this nature, where I'm trying to do expected value, I must know ahead of time every possible outcome. Secondly, I must know the probability of every possible outcome, and that's huge. So if I called this, and this is typical, capital X we'll use for the random variable, and then 2 would be little x1. 3 would be little x2, and so on. We use small x's for the individual things. Then the way we typically do this, because we're lazy in math, we don't like writing a lot of stuff, we say that the probability that big X equals any individual outcome, sometimes we just simply reduce it to this, and that's totally okay. If I'm identifying the random variable and I say, what's the probability my random variable takes on the value of 6? You can just say, what's the probability of 6? And then we typically will put this is capital P. We typically will put a little p. So P1 would be the probability of this particular outcome. Little p2 would be the probability of this particular outcome. And I hate it that we're using the same letter, capital X, little x, capital P. But this is a function, capital P. What is the probability of the following outcome? This is a scalar. This is the actual value. This is the probability of that particular outcome. So if I said, for example, I know there's only one way to roll a total of 2. So if I ask what's the probability of 2, which by the way is the same as saying what's the probability that capital X equals 2, since there's no ambiguity whatsoever in this context, just go ahead and write that. This would be what in this case? Well, if there's only one way I can roll a total of 2, then clearly this would be 1 over 36. But if I asked what's the probability of rolling, let's say, a total of 5, well, I have 1, 2, 3, 4 ways of doing that. So this would be 4 over 36 and so on. So I can clearly identify the probability of each individual outcome. And we're going to do that in a moment. So with this said, the way we formally state it is we say capital E, the expected value of my random variable. I have an experiment. In this case, it's roll the dice and add the 2 dice together. The expected value of that outcome is equal to, let's say there are, let's make it simple. Let's say there are n outcomes. Then it's the sum from I equal 1 to n of little xi, little pi. This is the formal definition of expected value. It's the actual total multiplied by its individual probability. It's actually that simple. And most of the time, you're not going to have so many outcomes that this becomes long, tedious, and cumbersome. Most of the time, this is actually a fairly simple calculation because in the real world, in real life, there might be very few possible outcomes. Now, the probabilities are not going to be the same typically. Okay, so let's do this very specific problem. So I put the dice roll chart up here just so we'd have something to work with. So let's do this. Let's say here's the random variable. Here's the probability the random variable equals the individual outcome. Okay, so I have 2, 3, 4, 5, 6, 7, 8, 9. Sorry, you gotta write a little bit smaller. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, the next part's easy. There's only one way I can roll a total of 2, so that would be 1 over 36. There's 2 ways, so 2 over 36. There's 3 ways, so 3 over 36, and so on. We've done this before. 7. Now, 7 is the most likely of all of my outcomes. There are more ways to get a 7 than anything else. So now when I continue, the numbers start diminishing. 8 then would be 5 over 36, and the 9 would be 4 over 36, 3 over 36, 2 over 36, and finally 1 over 36. So now the question is, if I roll the dice exactly one time and I add up the total, now we know there are many outcomes and we know all of the probabilities. Now remember, each individual roll, the probability is 1 out of 36. But since 6 of these individual rolls will add up to a 7, the probability of a 7 is higher than the probability of the other numbers. So we don't say the probability of rolling a total of 7 is equal to the probability of rolling a total of something else. No, the probability of rolling any particular combination of numbers is the same. But once I add the numbers, the probabilities change because there's more than one way of doing certain things. There's only one way of doing these guys. So finally, if I wanted the expected value, what is the expected value of my dice roll? It would be 2 times 1 over 36 plus 3 times 2 over 36 plus all the way to the end. And then eventually I'd get 12 times 1 over 36. Okay, so make it easy. Let's just multiply, add all the way down. Let's just take a moment to do this. You're going to like this. Now, if you're lazy like me, 2 times 1 plus 3 times 2 plus 4 times 3, and then when you're all done, then put everything over 36. It's a little easier because all of them have a denominator of 36. So we're all doing this calculation. We're multiplying, we're adding, we're multiplying, we're adding. And at the very end of the calculation, anybody want to venture an answer? So it'd be 2 plus 6 plus 12 plus 20 plus 30 plus 42 plus 40 plus 36 plus 30 plus 22 plus 12 all over 36. The answer is 7. If I roll the dice and I add them together, the expected answer is 7. Does that mean I'm going to get 7? No. That's the most likely outcome. It's not only the highest probability outcome, but think of it another way. Take every single one of these, 2, 3, 4, 5, 6, 7. Take every one of these, take their sums and add them up. The average is going to be 7. So that expected value is the average in a sense. Now, another way of thinking about it, and this is using something called the law of large numbers. I want you to roll the dice, look at the total, write it down. Now I want you to do it again and again and again and again. I want you to do it hundreds of times. I want you to do it 1,000 times. I want you to do it 1,000,000 times. What you're going to find is if you take an average of all of the outcomes you got, you're going to get a total of 2. You're going to get an 11. You're going to get a 12. You're going to get the extremes. You're going to get a lot of 5, 6, 7, 8s. But if you took the average of all of your outcomes with a ridiculously large number of trials, that's what it's called. Every time you do it, it's a trial. If I have a ridiculously large number of trials, you're going to see your numerical average is going to be really close to 7. Will it be exactly 7? No, but it's going to be really, really close to 7. And if everybody in the class is doing it, now we take the average of everyone in the class, that number is just going to stay right around 7. The expected value is actually what I will see if I do the experiment over and over again. Again, that's called the law of large numbers. It also refers to the asymptotic convergence I will get by doing this 1,000,000, 1 bazillion times. Technically, it's a limit. And so this is the first and the simplest execution of this particular concept. So if we're rolling the dice, now let's suppose I rolled the dice, or let's say, I'm sorry, I have like 3 in my hand instead of 2. Ooh, then I could have 1, 1, 1, 1, 1, 2, 1, 1, 3, and so on. And we could do this same problem again and look up all of those probabilities. And what we would find is the average of my rolls is going to be the expected value again. So let's do another problem, very simple problem. I want you to roll a single die, just one die. One die has 6 faces on it. And the faces are I can have a 1, a 2, a 3, a 4, a 5, or a 6. You're going to roll one die, assuming it's a fair die, okay, not a weighted die or something, crazy. Well, I'm pretty sure then the probability of each of these outcomes would be 1/6. So you get to roll the die exactly one time. What's my expected outcome? What is my expected number? What do I expect to see? Well, basically the answer is okay, that's going to be my outcome. And what will that be? Anybody? Just go blurt it out. That's an easy one. 1 + 2 + 3 + 4 + 5 + 6 is 21. So this answer is going to be 21/6, or exactly 3.5. But if I roll the die one time, I can't actually get 3.5 as an outcome. That doesn't matter. That's my expected outcome. It's the average of all of those rolls. Clearly, okay, so the expected answer doesn't necessarily have to be a possible answer. Well, then that doesn't make any sense. Well, ever since I was a kid, I always remember when they were talking about the census and they say the average American family, I don't know if you guys remember these kind of things. They'd always say the average American family has 2.2 children. How do you have 2.2 children? I'm pretty sure there are no families anywhere with 0.2 children. That was the average of all the families. Okay, so the average of every possible roll of one die is exactly 3.5. So another way of thinking about this, I want you to roll the die one time and write it down. Now do it again. Now do it again. Now do it again. Do it 100 times. Now, what is the average of all of the single rolls you did? It's going to be right around 3.5. That's what that means. That's the long-term average, the expected outcome. But the expected outcome, you can only do it one time and still talk about the expected outcome. So this type of probability experiment is actually easy to work with. Now, one of the main areas that this is used for, believe it or not, is every form of financial planning. Every type of retirement planning, every type of investment is completely and 100% based on expected value. In other words, I'm going to invest my money because I know what the going rates are. I know what the going returns have been. Therefore, if everything holds to form, if all the investments I'm doing are getting the same returns they got yesterday or last week or last month, then I can expect to earn this much money. Now, the thing is things are always changing and always in flux. So nothing ever stays the same for a long period of time when it comes to things like investing and retirements and stuff. You know, if you're going to play the stock market or you're going to do things like that, where else does this imply? Absolutely. Gambling. All forms of gambling is entirely based on expected value. If there was no way you could win, then you wouldn't bet money. But if you said, oh, I can win, here's what's going on. Okay, what can I expect? Now, here's one of the interesting things about gambling. And I don't mean gambling on sporting events. I mean, you know, playing cards, or, you know, I could just be gambling, flipping a coin, something where the probabilities are actually predictable. If you have a gambling game and you know what the probabilities are, you actually can calculate the expected return. So I'm going to use the simplest of all and the oldest of all gambling games. This is a good trivia experiment. If you ever get on one of those, you know, TV game shows or something, you know, what's the Jeopardy or something? Does anybody know what the oldest game of chance actually is? Supposedly, historically, anybody want to try it? Might surprise you. The oldest known recorded game of chance, gambling game. Come on, take a chance. What do you think? Anybody? Anybody? Roulette. Roulette is supposedly the oldest game of chance. They're thousands of years old. Roulette, that's where you have the numbers and you spin the wheel and you throw the little marble and it lands in a spot. Well, the interesting thing about roulette, of all of the gambling games that exist, like if you went to a casino, it has the highest probability of you winning. And there's no skill whatsoever. It's just a random guess. You're right. So a typical roulette wheel will have 36 numbers. I'm going to go up to 36. And then they'll have generally 2 neutral spaces. Okay, so the numbers 1, 2, 3, 4, 5, 6 up to 36 generally will alternate red, black, red, black, red, black. And that means there's 18 black numbers, 18 reds, and then 2 neutrals. So overall, there are 38 outcomes. So the way it works is you spin the wheel and you throw a little metal marble and it just bounces around as it slows down, you know, kind of like Wheel of Fortune, I guess, or something, and it lands in a spot. So you say, well, if I said before that you spin the wheel, I'm going to bet my money that it's going to land black. I'm going to bet my money it's going to land red, or I can bet my money that it lands on a particular number. But if I bet my money that it lands either black or red, there's 18 out of 38, which is approximately 0.47. In a roulette wheel, you will win, if you bet on a color, you will win about 47% of the time in the long run. In other words, your probability of winning is around this, pretty close to 0.47. So if you played 1,000 times, you can expect to win about 47% of the time. But what if you win on the very first try? Well, then, you know, walk away. You're going to maximize your winnings. But the interesting thing is you can't win 50% of the time. There is no game of chance that you can win 50%. And think of it another way, if it were possible for you to win 50% or more, then the casinos would go broke really fast. They can't afford to do that. You know, they need to win most of the time in order to stay open. So the expected return, okay, if I start with the probability and then I say I'm going to play this game a certain number of times, how many times can I expect to win? Now, this brings up a different type of problem. And we talked about this last day, just briefly. That's called a binomial experiment. Binomial experiment. And I mentioned this last day. I don't mean the binomial formula. I mean, a binomial experiment means there's only two outcomes. Anybody remember that? And what are the two outcomes? Let's see if you were paying attention last day. In a binomial experiment, there's exactly two outcomes. Oh, come on. Somebody's got to have this one.
1 or 0.
Success or failure.
Success or failure. That's it. Now, it depends what you're counting. So if I'm flipping a coin and I want to count tails, then I'll call tails a success and heads a failure. It doesn't mean you failed. It means you failed to count that particular thing you're counting. So it could be pick a card, any card, right? I'm going to call, a red card a success, a black card a failure, or a face card a success and a non-face card a failure, because you're counting successes. So if you're not a success, yeah, it sounds so ruthless. Well, no, it's what happened. You could say ones and zeros, 1 when it occurred, 0 when it did not. But a binomial experiment basically means there's only two outcomes. But when you're rolling the dice, there's so many outcomes. Oh, so I have to identify my success clearly. Maybe my success is I rolled a multiple of 3. Maybe my success is I rolled an even total. Maybe my success was I rolled a sum greater than 9. I don't know. Whatever you're calling your success, now you can easily calculate that. So binomial experiments, you have success and failure, and you have probabilities. Now, in a binomial experiment, what makes it binomial, first of all, is that the probability of success and failure never changes. Therefore, if we're doing the pick a card, any card, and you pick a card and you pull it out of the deck, the probability the next round will be different because I have fewer cards. So that cannot be a binomial experiment. But if we said pick a card, any card, and then you put it back in the deck and we reshuffle them, now my probabilities will remain the same because I still have 52 cards. So if it's cards, it has to be with replacement. If I'm flipping a coin, I have to be flipping the same coin. I'm not going to keep, swapping in new coins of different weights. But a binomial experiment, again, there's success and failure, and the probabilities are known ahead of time. Next thing is, no outcome can affect another outcome. So in other words, when I flip a tail, the next time I flip, the coin doesn't say, last time I landed a tail, I think I need to lean the other way this time so I make sure I land a heads. Nope. Each time you do it, it starts over. So if I said, what's the probability of a head? It's 0.5, regardless of how many heads I've flipped or how many tails I've flipped. So we say they're independent events. And lastly, in a binomial experiment, you have to know how many times you're going to do it before you start. So coin flip, I'm going to flip the coin 3 times. Okay, so let's do a really simple example of this. We're going to flip a coin 3 times. Oops. Flip a coin 3 times. What we generally do is we call little p is the probability of success, and little q is the probability of failure. These are the universal symbols we use in statistics. And clearly, p plus q must add up to 1. Okay, so in a coin flip, which makes life really easy, is that p and q are equal. We love that. But if I was rolling the dice, that wouldn't be the case. It wouldn't be 1/2. It'd be something else. So I'm going to do the experiment 3 times. So in this example here, my n is 3. Now, we're going to make it easy on ourselves. So what are my possible outcomes in this case? Well, my possible outcomes, let's say we want to count the tails. Okay, so I'm going to count tails. Well, first of all, if I flip a coin 3 times, what are the possible outcomes in terms of numbers of tails? In other words, I don't want head, head, head. I want, if I'm going to flip the coin 3 times, what are all the possible values I can get for numbers of tails? Anybody want to try that one? What would my random variable be? If I did head, 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 how many tails did I get? None. What else could I get if I flip a coin 3 times? These would be all the possible outcomes I could get if I'm counting tails. Now, the probability of each of these. Oh, now we've done this problem before. So here's where knowing, okay, let me write it down. My sample space is going to be head, 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 tail, head, tail, head, head, tail, tail. Tail, head, head, tail, head, tail, 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 head, tail, tail, tail. Okay, I know that's my sample space. That's why I only did 3 flips, so I could easily keep track of this. So what is the probability of 0? I'll just write it right underneath. What is the probability of 0 tails? Well, there's only one way I can get 0 tails, and there's 8 possible outcomes. And we agree these outcomes are equally likely. So this would be 1/8. Okay, 1 tail. There. There's 3 ways I can get 1 tail. And again, they're equally likely. So 3/8. 2 tails. 1, 2, 3. And 3 tails. Now, real quick check, my probabilities do in fact add up to 1. That's a good thing. So I'm going to flip a coin 3 times. What is my expected number of tails if I flip it exactly 3 times? Well, the expected answer will be 0 times an eighth plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. So that'd be 3/8 plus 6/8 plus 3/8. That's 12/8, or exactly 1.5. I'm going to flip a coin 3 times, a fair coin. I'm expecting exactly 1.5 tails. In other words, I'm expecting exactly half the time to get a tails. Now, I'm not going to do the formal proof here. The formal proof, I believe, is actually in the textbook. It's just kind of long-winded. It's not complicated. I actually do the formal. Well, I don't do the whole proof in a stats class because the math backgrounds are not consistent. But in a binomial experiment, okay, in any binomial experiment, you did n trials, and the probability of success is little p, and little p is a constant. Then the expected outcome in all binomial experiments, and this is one of the single most important formulas in all of statistics, by the way, it's NP. So if I flip the coin 3 times and the probability of success is 0.5, 3 times 0.5. So if I flip a coin 1,000 times, the expected number of tails would be 500. That's sort of the common sense approach, but it's actually the mathematical approach. And I'm not going to do 1,000. That might take us a while. But if I said, okay, flip a coin 1,000 times, I can get 0 tails, very low probability, 1 tail, 2 tails, 3 tails, all the way up to 1,000 tails. Now let me calculate the probability of each of these outcomes. Now let me multiply the outcomes by the probabilities and add them all up, and it's going to add up to exactly 500. That's an absolute. In a binomial experiment, that's one of the reasons we love binomial experiments. Because in a binomial experiment, again, if I know n and I know p, I already have the expected value. I know exactly what to expect. So with that said, I can do calculations really, really simply. So investment situations. So I'm going to give you a really simple example of an investment situation. All right. Let's suppose, and I like to use this example. Let's suppose you're a carpenter. Okay. And every day you work, you're guaranteed to make, let's keep it real simple. Every day you work, you're guaranteed to make $1,000. But days you don't work, you're going to lose, let's say, I don't know, let's say you're going to lose $500 because you have overhead and you have to pay people anyway. Okay. So you make $1,000 on the day you work, on the days you don't work, you lose $500. So in this case here, you're going to either make $1,000 or you're going to lose $500. Say, well, how can I lose money? Oh, you're a carpenter and you live in Seattle. So in other words, you can't work in the rain. I'm from a whole family of contractors. There's a few things you can't do. You can't be doing construction in the rain because everything, open up a house and it's raining. Nope, doesn't work. So I want to know for the next week how much money I can expect to make. Well, there's one thing that's really important. The rain. So what I do, that I always laugh, because I would say every 2 or 3 days I go to the San Diego weather and I look for the week to see, hey, is it going to rain this week? And it usually says, every day 0%, 0%. So yesterday, by the way, it said 0% chance of rain on Saturday night. And then of course it drizzled and light rain and rained overnight. So I don't even know how accurate that is. But let's suppose, okay, this next week, Monday, Tuesday, Wednesday, Thursday, Friday, the probability of rain, when we look it up, and let's say this is accurate. The probability of rain on Monday, let's say, is 0.6. On Tuesday, it's it's not 8. 0.8. On Wednesday, it's only 0.2. On Thursday, it's 0.5. And on Friday, let's say it's, I don't know, different, 0.7. This is Seattle. Okay, I've been to Seattle. It basically may rain every single day of the year. So let's say these are the probabilities of rain each day. Okay. What is my expected return for the week? What can I expect this next week? How much money can I expect to make or lose this week? For example, if it rained every day this week, I would lose $500 every day. If it didn't rain any day this week, I would make $1,000 every day. So I can do anything from losing $2,500 to making $5,000. But there are no days where the probability of rain is 1 or 0. Okay, so what is my expected return? So I'm only going to make money. Remember, I'm only going to make money if I work. I'm going to lose money if I don't. So I'm going to make money when it doesn't rain. I'm going to lose money when it does rain. So day one, by the way, we have 5 different days. So what is my expected return just on Monday alone? Well, I'm going to make $1,000 with what probability? Anybody? What is the probability?
60% or 0.6?
Careful. That's the probability of rain.
40%.
Yeah, 0.4.
40%.
Yeah. By the way, at no point in your life do you ever use a percent in a probability problem. Some of you have gotten really bad habits. Percent is how I express something in using English. You don't use percents. You use probabilities, which are, decimals between 0 and 1. Remember, percents are 100 times probabilities. You got to be really careful when you're using percent. If I wrote, 40%. No, write 0.4. Don't use 40%. Yeah. We speak in percentages. We don't do math in percentage. Percent is how I will, there's a 40% likelihood of the following thing happening. But I don't say my probability is 40%. Percent isn't probability. Apples and oranges here. Now, I'm going to lose money. You can write minus 500 or plus negative 500. Actually, that's probably better form to write like that, with a probability of 0.6. Now, that's just Monday, by the way. That's not every day. Now, I'll write it under because it'll make it easier. Now, Tuesday. You guys get what's the probability I'm going to make $1,000 on Tuesday?
0.2.
Yeah, remember, I'm giving, this is the forecast. And I'm doing this on purpose because this is, when I'm looking up the forecast, it always gives you the probability of rain. It doesn't give you the probability of no rain. Oh, okay. So when you're saying, you're looking online and it's saying, and in words we say, there's an 80% chance of rain tomorrow. There's 100% chance of rain tomorrow, right? That means there's certainty. So this would be sorry, got that backwards. This is 0.2 and that's 0.8. Those probabilities obviously have to add to 1, and that is really important. And this day will be, now we flip them, 0.8, 0.2. This day will be 0.5. Can't really mess that one up. 0.5. And then this day, 0.3. And 0.7. So let's add these up, will you? Everybody on your own for a moment. Let's do this on your calculator. All right, let me know when you got an answer. I got an answer. When you get it, just holler it out.
800.
$800. That's what I got too. I know I did it right because Zach got it. Now, you say, but wait a minute, I either make 1,000 or I lose 500. That 800 is not an outcome. No, no, no. It's the expected. Okay, so I live in Seattle. I make $1,000 every day I work. I lose $500 every day I don't work, Monday through Friday. Okay, that means on average, if this was a typical week, on the average, then I make $800 in the week. Oh, that's a totally different thing. Yes, it is. It's a totally different thing because that's the expected return. Now, I'm giving you an overly simplified example. I'm only giving you two outcomes, but generally speaking, this is how most investments work. So you want to invest money, you go, oh, if that company takes off, I don't know anything about investing. So, maybe it's Bitcoin or something. If that takes off, I'm going to make money hand over fist. Oh, but if it flubs up and fails, I'm going to lose everything. So therefore, when I'm investing, do I put all of my money into that one risky investment? Would that be wise strategy? If it works out, I'll be rich. And if it doesn't, I'll be broke. I'll put everything there. Do people do that, by the way? Do people put everything there? See, Ben Franklin had a quote. Anybody know what it is? Ben Franklin. Don't put all your eggs. Anybody? Come on, finish it.
Basket.
Yeah. Do you know what that refers to? That refers to investing. That was in the 1700s. Yeah, that was common wisdom. You do not put everything. Now, if you had an absolute guarantee that you were going to make money, if it was perfect, you couldn't lose money, well, yeah, then put everything there. But the expression "don't put all your eggs in one basket" refers to investing. If you put everything in one place and it doesn't work, you're done. So you have strategies. Okay, so what you do in reality is, I have this really risky investment, but if it works, I'm going to make a lot of money. Then throw some money there, but don't put it all there. But also some of your money, well, I have this really, really safe investment, but it doesn't make a lot of money. Yeah, but you definitely put money there because you can't lose there. So you spread it around. And by the way, if you have financial advisors, they're constantly spreading it around and moving it around almost on a daily basis, so that they're trying to always get the most return. Okay, that's what people do. And so it's all based on expected return. Now, is this absolutely flawless? Do I know everything? No. And for example, we don't know that it's going to rain tomorrow, but we're using probabilities of outcomes. Okay, so now you're a card player. Okay, you're a card player, and you say, "Here's the cards in my hand," whether it be poker or blackjack or anything, or go fish. You're playing with the cards. Well, I need a certain card. That doesn't mean you're going to get it, but you can actually do basic probabilities and saying, we only have one deck of cards maybe, and some of these cards have already been played. So what's the likelihood I can get that next card? It does matter. Okay. So expected value, once again, is if I know the probabilities, and that's it. I have to know the outcomes and I have to know the probabilities. If I don't know all the outcomes or I don't know all the probabilities, then there's nothing to calculate. Okay, so one of the simplest and most common examples of expected value, and one I like to always ask and throw on a quiz, is a raffle. Okay, now most of you are familiar with raffles to some degree. So I have an organization, we're trying to raise money, let's say, it could be a hospital, could be anything. And I'm going to sell raffle tickets, and you're going to pay money for the raffle ticket. And then at the end, we put all the tickets, you get your half and I, keep the other half. And we put them on in a big bin and mix it around, and I pull a name or I pull a number out, and that person wins a lot of money. Now, obviously, at the end of the raffle, the idea is not to give away more money than came in. The idea of a raffle is to actually, make some money for, but it could go either way. Okay. So if I'm doing a raffle, and you want to buy a raffle ticket, do you expect to make money? Do you expect to lose money in the long run? And it might be one of these things where they do the raffle every week. At my wife's school, what they do at all of the football games and basketball games, well, at least pre-pandemic, was they literally would go around during the game and selling raffle tickets, but it was something like $2. And then what they did at the end, they drew a name and you got exactly half of whatever the money was. And the other half then went to whatever it was. It could be for funding the girls' basketball team or the boys' football team or something. And it was a really simple, easy way to generate some revenue for those sports. And everybody in the audience knew half the money was going to the sport. But I could still come out. They had a few hundred people buy tickets, and I win. I make a few $100. So let's say that we have, let's keep it really simple. We have 100 raffle tickets are sold at $1,000 each. Okay, we're going to keep it small, kind of like a, a fundraiser kind of thing, right? There is one first prize of how about of $50,000. There are two second prizes of how about $10,000. There are 10 third prizes of $1,000. Okay. Actually, let's make it 1,500. Yeah, actually, make some money. Okay, that's it. Well, that's actually a lot of prizes. 13 people are going to win, and only 100 people bought tickets. So now you want to buy a ticket. What is the expected return? Are you going to make money or are you going to lose money? Well, you might win first prize, but most of the folks aren't going to win anything. Okay, so what are the possible outcomes after I've done this? Now, remember, you just spent $1,000. So if you didn't win the raffle, you just lost $1,000. So keeping in mind that you had to buy a ticket for $1,000, then what are my possible outcomes? Okay, you're about to embark on the raffle. All right, so what are all the possible outcomes? Is 50,000 a possible outcome? Can you walk away $50,000 richer?
49,000.
Yeah, you're only going to walk away $50,000 richer if somebody gave you the raffle ticket for free. No, you had to buy the raffle ticket. So you can't walk away $50,000 richer, but you can walk away $49,000 richer. And that's important you recognize that. Otherwise, the people who do the raffle are just giving the money away. Okay, what else is a possible outcome? Now that you got that one, the rest should be easy. What are the other possible outcomes?
9,000.
9,000. Keep going.
And $500.
500, and there's one more.
Negative 1,000.
Negative 1,000, which, by the way, will be the majority of people. These are so. In other words, before the raffle has occurred, you're just an innocent bystander, and you're going, I think I'm going to jump in. So after the raffle takes place, these are your possible outcomes. You can't walk away $50,000 richer because you paid the 1,000 before the raffle, was drawn. Oh, so if I'm not one of those winners, then that's me. Now, what are the probabilities of each of these? There were only 100 tickets. We are assuming everything's equally likely. We're mixing them up, and there's no cheating going on here. Well, there was one here, so this would be 1 over 100. Okay, there were 2 here, so this would be 2 over 100. There were 10 here, so this would be 10 over 100. And what would the probability of the last outcome be?
87 over 100.
87 over 100. Well, that's easy enough. So now my expected value would then be that product plus that product and so on. So I'll write it out. So 49,000 times 1 over 100 plus 9,000 times 2 over 100. And you guys can start calculating this. Plus, and then the last one is negative 1,000 times 87 over 100. So let's go ahead and calculate that. So 49,000. All right, does anybody have an answer? I got an answer. What is the expected return? Tell me when you get a number. Just holler out if you get a number.
Negative 150.
Negative $150. And you actually do want the dollars. So what does that mean? In simple English, what does it mean that the expected return of somebody playing this raffle is negative $150, since that isn't an actual outcome? you got to explain this to a non-mathy person. It might make it easier. Okay, 100 people just bought raffle tickets. Some won, most lost. What does this represent then?
That you're gonna lose the 1,000.
Well, but a negative 150 isn't 1,000. Think of it this way. Somebody did win. A lot of people did lose. If I take all 100 people who just bought raffle tickets and I said, what was the average? Okay, then the average of those 100 people is on the average, they lost $150 each, but some people won big. Most people lost because they didn't win anything. So whenever you buy, so let's say you're one of these people that plays the lottery every single week. Well, then you're losing $1 every single week, but somebody's winning. But the expected value of the lottery is definitely negative. Otherwise, they wouldn't keep it going if it was positive. So this represents the average outcome of all 100 people who played. That's another way of thinking about it. Here's another way that, again, this is the answer. This is how it's calculated. But how do you make sense of it? Think of it another way. $1,000, 100 tickets. That means $100,000 were spent. How much money was given away? 50, 60, 70, $85,000 was given away. $100,000 in tickets were sold, $85,000 in prizes were given away. That's $15,000 that the raffle people made. $15,000 divided by 100 people would be $150 per person. Okay, that's a way to justify this answer. It's much easier to just calculate the answer. Now, should you play this game? Okay, if you're a gambler, should you play? If you want to sit down at a slot machine, should you play? Well, if the expected value of every game of chance is negative, should I play? Well, don't people win? I mean, somebody wins. So the idea is if the expected return is negative and you know that, then you basically only play if you can afford to lose. That's the simple rule of thumb. You know, you've got so much money, you don't know what to do with it. Yeah, I'll go ahead and play the raffle because I might win. Yeah, I just have fun. I'll go and gamble at a casino because I might win. It'll be fun. But if you can't afford to play, then playing is foolish because if the expected return is negative, that means on the average, you'll lose most of the time. Will you win if you play? Let's say this goes on every week, this particular raffle. It's every week, all year, every year. You're not going to lose every time. Nobody has that bad. That's like saying I'm always flipping heads on a fair coin. You're going to win sometimes, but in the long run, you're going to lose on the average. Now, what if? Let me change one thing here. Let me change one thing. Let's see, where can I change? I think. Let me change this guy right here. I'm going to change this. I'll use a different color. Let me change this to 3,000. So instead of the prizes being $1,500, we're going to make that third prize $3,000. So what does that do here? That makes that 2,500. And then what does that do here? Where is it? Oh, right here, it makes this 2,500. What does that do to this?
Professor, why 2,500 if it should be 2,000?
I'm sorry, say it again.
Why is it 2,500? You said no, and not 2,000.
No, I'm saying I'm upping this from 1,500 to 3,000. Oh, I'm sorry. Oh. Thank you, Alexi. Oh, bad math. Thank you, Alexi. You're right. Yeah, that should be 2,000. Thank you. Good catch. I wanted to use a different color so you knew where the changes were. That's now 2,000. Thank you. And let me put it here. What changes? This is huge, by the way. Something absolutely changes. Well, obviously my answer is going to change, but what does my answer change to? It's kind of the last thought of the day today. What does my answer change to now? Anybody?
Zero.
Zero. Well, first of all, the organizers of the raffle did a lousy job because they didn't make any money, but zero. Huh. now should you play or not play, or does it even matter? The average outcome of everybody who played this particular raffle was 0. Now, the vast majority of the people lost. That's true. But the expected return is now 0. That kind of changes things. If I was a gambler, I'm not, but if I was a gambler and I went to a casino and they said the expected return on all of our games of chance, the expected return is 0. That means if I'm actually smart and I make good decisions, I might actually win, because some people will make bad decisions and then they'll lose. 0 changes everything. We have a name for this. If you are calculating the expected return, and we're talking, it's a money thing. I'm going to calculate the expected return on some, this is technically a game of chance, right? I'm blindly pulling a name out of a hat. We call this a fair game. So the definition of what's called a fair game is when the expected value of the random variable is 0, meaning in the long run, you're neither going to lose nor win. It's basically a break even for everybody. So if it's a fair game, these go together. So before we started, if I said, is this raffle a fair game, or is this a fair raffle? You would say, this one is. The first one isn't, because you're going to lose 150 on the average. Now, what if the expected return was positive? On any investment, what if the expected return was positive? Then should you, embark on that? Sure, because that means on the average, you're going to win. Now, could you still lose? Yes. You see, I'm going to sell these at 1,000 each. There's just going to be one prize. Now, I sold these at 1,000 each. That means we generated $100,000. 1,000 each. That might be a little bit uncomfortable for a lot of us to come up with $1,000. But what if I said the first prize was $1 million? Again, it's the philanthropist raffle. Okay, I'm going to sell 100 tickets at $1,000 each, and there's going to be one prize, and it's going to be $1 million. Should you play that game? It's a difficult question. Should you play that game? Should you buy that raffle ticket? What do you think? There's one prize of $1 million. Well, that means 99 people are going to lose, one person's going to win, but the average of the group is going to be huge. It's going to be a large expected value, large positive expected value, but most people are going to lose. Should you play that game? There's actually a simple answer to that. And it involves if. It's $1,000 to buy the ticket, but if you win, you win $1 million. Should you play that game? Anybody want to try that one? Because there actually is an answer. That this is investing in general. It's the same thing. Yes, if what? Anybody? Take a chance. Because most of you wouldn't play this game. Yes, if you can afford to lose 1,000. That's how it works. If you can afford, if losing the 1,000, in other words, you're not going to win. Most of you are not going to win. You bought the ticket for $1,000. If you can afford to lose $1,000, if that's not going to destroy you, right? That's not going to make you go broke. If you can afford to lose the 1,000, you should play, because the expected value is huge. The expected value, right, is what, $1 million. That means $900,000 among 100 people. That means the expected return is $9,000 on a $1,000 ticket, but only one person is going to win. So the rules of investing are always that if something is risky but has a great return, if it works, you say, yes, I will invest, but only if I can afford to lose that money. And so that's one of those things about investing. Most people are very safe, but investing is all about expected return. So we're going to do one more simple example of this. All right. So you and your buddy, you decide you're going to play a game, and it's just two people, you and one other person. And it's going to be real simple. You have a single die, and you're going to roll the die. All right. You and your buddy. And let's say the game costs, in fact, we're not even going to put a price on the game. We're going to make it really simple. If you roll let's say a 1, you win $50. If you roll a 2, 3, or a 4, your buddy wins. Let's say excuse me, $40. That means they pay you $50, you pay them $40. You're doing the rolling, you roll a 5, you win. Now let's say $120. And if they roll it, and if you roll a 6, tell me what must come here to make this a fair game. I want to play this game. I'm bored. It's kind of like you play any card game with a friend. You're playing, my wife and I play backgammon all the time. And, we each win about half the time. You're going to play this game with your friend. You're on a long cruise. It's really boring. And you're just going to play for hours and hours and hours. I want this to be a fair game, because if it's not a fair game, if one person has a positive expected return and the other one has a negative expected return, then over a long period of time, it's going to become really, really one-sided. Okay. So here's how it works. Again, I roll a 1, you pay me 50. I roll a 5, you pay me 120. I roll a 2, 3, or 4, I pay you 40. What's going to happen if I roll a 6 in order to make this a fair game? So I'm going to pause this just for a second, and I want you guys to figure